Look into the bowl of a shiny silver spoon, and your face is upside down. Turn it over, and your reflection is upright and shrunken. Funhouse mirrors stretch and warp physical proportions into unrecognizable shapes, yet these distortions follow predictable geometric laws that govern every curved reflective surface. To decode them, we have to recognize that a curved mirror is simply a slice of a hollow sphere. The dead center of that mirror slice is called the pole. If you draw a straight horizontal line right through the pole, you get the principal axis. Because the mirror is a piece of a sphere, it has a center point, known as the center of curvature. Exactly halfway between that center and the mirror's pole sits the principal focus. These specific landmarks dictate how light behaves. Any light ray coming in parallel to the axis reflects through the focus. A ray passing through the focus reflects out parallel. A ray traveling through the center bounces back along its original path. And a ray striking the pole reflects at the exact same angle it arrived. By combining any two of these ray paths, we can map the exact transformation of an image as an object travels toward the mirror. Let's track that journey on a concave mirror, one that curves inward. When an object is incredibly far away, at infinity, the incoming parallel light rays all converge directly on the focus. The resulting image is real, upside down, and microscopic. As that object moves closer, stopping just outside the center of curvature, the intersection of our light rays shifts. The inverted image creeps away from the mirror and starts to grow, though it remains smaller than the real object. When the object reaches the center of curvature, the reflected rays intersect directly underneath it. At this specific spatial landmark, the real object and its upside-down image are the exact same size. Push the object closer, between the center and the focus, and the image is forced further back. It now rapidly expands, becoming magnified as it moves beyond the center of curvature. At the focus, the behavior shifts. If you place an object exactly on the focal point, the reflected light rays shoot out perfectly parallel. Because they never intersect, the image vanishes to infinity. Now watch what happens as the object crosses the focus. The real rays diverge, but the brain traces them backward, behind the glass. The image is now an upright, virtual, and massive reflection. Looking at these standard ray diagrams, you can see how this geometry dictates the object's transition, from beyond C all the way down to between F and mirror. The intersecting lines show exactly how the image forms. The distance between an object and the glass is the only variable determining if the result is a real image or a virtual illusion. If we flip the mirror so it bulges outward, we get a convex surface. Here, the center and focus are trapped behind the glass, which forces light rays to scatter and diverge when they hit the surface. Because the rays always spread apart, they only ever intersect virtually. No matter where an object stands in front of a convex mirror, its image remains shrunken, upright, and locked behind the glass. Physicists track these shifting positions using the Cartesian sign convention. We place the mirror's pole at 0. Distances measured in front of the mirror, against the incident light, are negative. Anything appearing behind the mirror is positive. This convention plugs into the mirror equation. By calculating the relationship between image distance, v, object distance, u, and focal length, f, we can pinpoint image locations without drawing a single ray. These mathematical formulas quantify the physical geometry we've just witnessed along the principal axis. This specific geometry is applied everywhere. In a car headlight, placing a light source at the focal point of a concave mirror creates a perfectly parallel beam that cuts through the dark. This radio telescope uses the same physics. The massive concave dish intercepts weak, parallel radio waves from space and funnels them directly into a single receiver suspended right at the focus. We also utilize the virtual image formed inside the focal length. By placing a tooth within this range, a dentist's concave mirror provides the upright, magnified view needed for precision work. Convex mirrors use diverging rays to compress a massive area into one small panel, allowing security guards to view entire store aisles or blind turns from a single location. The James Webb Space Telescope applies these laws 1,000,000 miles from Earth. 18 gold-coated mirror segments gather incredibly faint infrared light and bring it to a pristine, calculated focus. These surfaces are precision instruments, allowing us to manipulate light by applying these geometric laws from the kitchen table to the universe's edge.